Okay, the Laplace transform is a tool for solving differential equations, and basically we use it as a tool to convert calculus like differentiation and integration to algebra, because we from differential equations we get algebraic equations using the Laplace transforms. And I gave you a list of the most important Laplace transforms. Well, I'm not going to repeat that today. And I talked about the properties of the Laplace transform, and which was one of the most important properties was the Laplace transform of a derivative. By the way, we show this as the Laplace transform of f of t, like this. The Laplace transform of a derivative of a function is s times f of s minus f of 0. F, small case f, is the time function. Capital F is the Laplace transform function. By the way, s has a unit of frequency, 1 over time. That's one more thing. Similarly, you can take the derivatives of higher derivatives can also be expressed by the Laplace transform. And another thing is that the Laplace transform of an integral, we said, is f of t dt is f of s over s. So you see, differentiation and integration are converted to algebraic terms, and that helps us solving the differential equations. And I gave you and started giving you an example, which was the following. It was y double dot plus 3y dot plus 2y equals 2f of t. And we assume that there are no initial conditions, so that you can write, just look at the previous notes, y of s can be written as 2 over s squared plus 3s plus 2 times f of s. Now, if you take f of t, which is the forcing function, let's say, 1 for t greater than 0, which is a step function. Okay, in which case you can take its Laplace transform, and this will be 1 over s. F of t step function's Laplace transform is 1 over s. So y of s can be written as 2 over, and we can factor this. It becomes s plus 1, s plus 2, and this f of s is 1 over s, so I put it here. And then we can express this as partial fraction expansion, a over s plus b over s plus 1 plus c over s plus 2, we said. And we can find ABCs by the regular equating the numerators and denominators. That's one way of doing things. From which you will find that, what will it be? I don't remember. I think A was 1.
Hojam, A was 1, B was -2, and C was 1.
It was 1, okay. So that y of, you can write this as equals 1 over s minus 2 over s plus 2 plus 1 over s plus, no, sorry, 2 over s plus 1, 1 over s plus 2, from which you can take the y of t is the inverse transform of y of s. This can be easily inverted from the tables. 1 minus 2e to the minus t plus 2, not 2, 1 e to the minus 2t for t greater than 0. That is the solution. We know this. But this is what you have learned in the differential equations class, actually. But there is a kind of an easier way of doing the partial fraction expansion, which probably you have not seen, so I will show it to you. So the partial fraction, let's say, expansion, which I will PFE, let's say, is the shorthand. Let's say that you have a general function like y of s equals a numerator polynomial divided by a denominator polynomial. Okay, I don't know why this happens, but it's okay. So it is a polynomial in let's say bms to the m plus blah 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 b1s plus b0 is the numerator polynomial, and you have s to the n plus, let's say, a n minus 1, s to the n minus 1, etc., etc., plus a1s plus a0, let's say. So this is a regular polynomial Laplace transformed expression. Now you cannot take the Laplace transform of this, so you want a simpler expression, which you will write as the following. Let's say k1 divided by s minus p1 plus p2, etc. plus, let's say, kn s minus pn, where pi are the roots of p of s equals 0. Okay, they are the roots of that polynomial. Now we want to find k values. K's are the partial fraction expansion coefficients. We want ki. Now the problem is you can do it as you equate the numerators and denominators, but there is an easier way, which I will show it here. If you want, for example, ith coefficient, okay, what you do is you multiply s minus pi, whatever that pi is, with your f of s, and where you evaluate this thing, s equals pi. Okay. Now, remember that this is n of s divided by s minus p1, s minus p2, s minus pi, s minus pn. Okay. So s minus pi is one of the roots of this equation. So when you multiply f of s, sorry, I said f of s, right? This should be y of s, sorry. When you multiply y of s by s minus pi, these terms cancel so that there is no division by 0, so that you are going to get the ki value. And Ki is called the residue of y of s at pole. We will see this term s equals pi. Okay. So you can very easily find the values of these coefficients. For example, in our case, let's try to remember it. What was it? Y, sorry. Equals, let's say, I will use K1 over S plus K2 over S plus 1. Instead of ABC, I use K's here. It doesn't matter, it's the same thing. K3 over S plus 2, okay? Now, K1 is Y of S, S times Y of S, evaluated at S equals 0. So I multiply it by S, so you get 2 over S plus 1, S plus 2. And you let this to be at S equals 0, so it is 2 over 1 times 2, which is 1, as we have done before. K2 is S plus 1 times Y of S, evaluated at S equals 0. So it is 2 over S times not S equals 0, I'm sorry. S equals minus 1, obviously. Minus 1. 2 over minus 1 times. Minus 1 plus 2 is plus 1. So it is minus 2. And K3 is S plus 2Y of S, evaluated at S equals minus 2. So it is 2 over S times, this is S equals minus 1, S plus 1, S equals minus 1, which is 2 over, not minus 1, minus 2, I'm sorry, this is minus 2. Minus 2 times, minus 2 plus 1 is minus 1, which gives you 1, okay? So, as you remember, this is what we had found before. This was A, this was B, this was C. The same result happens. This is the kind of a quick way of doing for the finding the residues of a transfer function. Okay, and it usually works. This actually works if the poles, which are the roots of D of S, are separate or distinct is the word for this. They are different if there are different roots. Now, there are cases in which they don't work. Well, it kind of works, but in a different way. Let me see, where is that? One case is that the repeated root case. You might have roots that are repeated. For example, you might have y of s equals, I don't know, 1 over, let's say, s plus 1 cubed times s plus 2 or something. Here you have this thing repeated. Root is for example, p equals -1 is, let's say, repeated 3 times here. In this case, this procedure we talk about doesn't really work very well. I just underlined this, by the way. It is not something extraordinary. Okay, in this case, what do we do? Well, let's say that, again, y of s, which is, again, a numerator divided by a denominator, is we can write it as a numerator, doesn't matter, but let's say you have s minus p1 to the power k. It is repeated k times, and you have s minus p2, s minus pn. You have different roots, but this p1 is repeated k times, the others are distinct, let's say. In which case, we can write it as follows. Let's say I will dk over s minus p1 to the power k plus b k minus 1 s minus p1 to the power k minus 1 plus p1 s minus p1. So this concludes the opening up of the multiple root. Then I will just write the other roots, a2 over s minus p2 plus blah blah blah. Let's say an over s minus pn. Okay, the non-repeated roots are not interesting. The non-repeated roots can be found a2 to an, let's say, to an can be found as before, let's say. Okay, there is no problem with that. But these bk coefficients are determined from the following. Well, this bk, the first one, is determined from the following. Let's say y of s times s minus p1 to the power k, evaluated at s equals p1. This is as usual, okay? This is kind of the general formula. Then bk minus 1, the second one, this one, for this you take the derivative of the above expression and evaluate it at d by ds of y of s times s minus p1 to the power k, evaluated at s equals p1. Okay. And the general expression for this is that it is bk minus I is simply 1 over I factorial Well, it is possible to prove this. I'm not going to spend time on this. If you are interested, again, you can just look at your book, or if you are interested, just ask me personally. I will show it to you, but I won't spend time on this. Okay. So you take the ith derivative in order to find the expressions for b of ki. So it looks very complicated, but usually it is quite simple. Let me give you an example here. Usually it is kind of gets simplified. Let's say y of s equals, let's say s squared plus 2s plus 3. That's the numerator. Denominator is s plus 1 cubed, let's say. Okay, so that we can express this. We cannot open this up by itself. It's not possible. You know, you cannot find Laplace transform. So you find a simpler expression. It is b3 over, let's say, s plus 1 cubed. Now this one, Laplace transforms of these can be found from tables. S plus 1 squared plus b1 over s plus 1. There is a question or something. Let me see. Come on, this is not the time. We can talk about it later. B3, this coefficient is simply y of s multiplied by s plus 1 cubed, evaluated at s equals minus 1, which is s squared plus 2s plus 3, s equals minus 1, which comes out to be 2. B2 is simply the derivative of this. Is d by ds of s squared plus 2s plus 3. So it is 2s plus 2 which is what? 0. Which is the derivative of this, which is 2, evaluated at s equals minus 1, which is 2. No. There is a 1 over 2 factorial, I'm sorry. 1 over 2 over 2 is 1. So, y of s is simply 2 over s plus 1 cubed plus 1 over s plus 1. Y of t, if you take the Laplace transform from the tables, you will see that this is 2 t squared e to the minus t plus e to the minus t. So this will be 2t squared plus 1 minus t for t greater than 0. Okay. So this is kind of the way you deal with this problem. The way we do it, by the way, how did I transform this? I have to write this down. For this one, there is in the Laplace transforms, the Laplace transform of t to the n e to the minus at is 1 over n factorial 1 over s to the a to the power n minus 1. This gives us the following result, okay? The following result. Okay, so repeated roots are done by, as I said, by taking derivatives. A special case is the complex conjugate poles. Poles, or I can say roots if you like. You probably have seen this again in differential equations, but I have to repeat it. Now, the poles are roots, let's say, of the denominator, d of s. So you have y of s equals, again, n over d, n of s over d of s. D of s has complex conjugate poles, where P1 is, let's say, minus A plus JB. And if you have a complex pole, there will always be the conjugate of that. A plus JB will be the conjugate pole of that. Now, J, we use J as the square root of minus 1. This is the electrical energy. This is the standard notation usually.
Hocam, isn't it should be minus one of them? Minus JB.
Ah, yes, sorry. It should be minus. This means complex conjugate plus the real parts are the same. The complex parts are conjugate. Okay. Now, as a simple expression, let's use the following. First of all, if the poles are complex conjugate, you can separate them to complex conjugate ones and the real ones. The real ones, we deal them as before. Let's talk about the complex conjugate ones. Let's say you have n of s over d of s, which is n of s over, let's say, s plus p1, s plus p2. Okay, p1 and p2 are these, by the way. So it is n of s divided by s minus a plus jd, s plus oh, okay. So if you multiply them, by the way, why do we deal with this? We can do the complex conjugate poles just as we do the regular poles, but then we will have to deal with the complex mathematics. And we don't really want to deal with the complex mathematics that much, because it gets kind of complicated and you can make errors and so on. So it is better to do it this way. It is s plus a squared plus b squared. So if you have two complex conjugate poles, you can write your equation as follows. That is, you can write it as a square of the real part with s and a square of the imaginary part like this. Now we know that we can use these in order to obtain the back transformation. Remember the following. This is important and we have to remember it. e to the minus at cosine, let's say bt, has a Laplace transform of s plus a divided by s plus a squared plus b squared. And e to the minus at sine bt has a transform, Laplace transform of b over s plus a squared plus b squared. Now, the thing we need to do here is somehow to express our function resembling these things with certain coefficients in front of them. So we will try to express our y of s, which is this one, this function, okay? Look like these things, this one, and this one, with some coefficients in front of them. Okay, if you can do that, in that case, we will be able to obtain the Laplace transform of the complex function. That is the easiest way to deal with the complex conjugate roots. If otherwise, if you try to deal with complex conjugate roots using complex mathematics, you usually get into trouble. So this is the, as I had told you, you should be trying to do this. Let me give you an example here. Let's say y of s is 1 over s times s squared plus s plus 1. Okay. And as you see, this is, there's a real root at s, which I will call a over s, plus, now there is a second order root, which is s squared plus s plus 1. At the top, I will just put bs plus c here, okay? Now, this a can be found easily from s times y of s evaluated at s equals 0, which is 1 over s squared plus s plus 1 evaluated at s equals 0, which gives you 1. Okay. Now for bs plus c, you cannot do that. It's easiest if you equate the coefficients and denominators. So for example, what you do is something like, since a is 1, 1 is equal to a times a is 1, a equals 1 times, let's say, s squared plus s plus 1 plus s times bs plus c. Okay, so they are equal. So what do you get? 1 equals, s squared is here, bs squared plus 1, b plus 1s squared, right? Plus, there is cs here, c plus 1s plus what? 1. 1 is 1, but b plus 1 equals 0. This will be 0, this will be 0. So b equals minus 1, c equals minus 1. So our function now becomes, therefore, y of s is simply 1 over s minus s plus 1, s squared plus s plus 1. Okay. Which is 1 over s times minus. Now s squared plus s plus 1, let's try to find the roots of this. This is roots of this is P1 and 2 are minus 1 over 2 plus minus J root 3 over 2. Okay, it is like cosine and sine 30. So I can write this as follows. Again, s plus 1. S plus 1 over 2 to the power squared plus root 3 over 2 squared. Okay, it is the same thing. You try it, you will see that it is equal to s squared plus s plus 1. Okay. Now the only thing is I want to write this so that I will be able to obtain the above expression, these expressions, if you remember. Okay, let me just try to copy them. So, well, okay, let's keep it up here. I want to write the following. S plus A, which is 1 over 2. Okay. So I can write it as follows. Y of S equals 1 over 1 over S is there. It's easy. Minus. Now I want S plus 1 over 2. S plus, there we have S plus 1. So I can write it as S plus 1 over 2 plus 1 over 2. Then you have S plus 1 over 2 plus root 3 over 2 squared. Okay. So I can write this as 1 over S minus S plus 1 over 2. Again, the same thing. S plus 1 over 2 squared plus root 3 over 2 squared. But I have a minus 1 over 2 term left here. So let me write this down. But I don't want 1 over 2. I want root 3 over 2 there. So 1 over 2, let's write it here. But I want a root 3 over 2. Again, the same thing. S plus 1 over 2 squared plus root 3 over 2 squared. Now I have added a root 3 over 2, so I have to divide to root 3 over 2. This is a minus, by the way. It's not
Hocam after 1 over S minus S plus 1 over 2 square olacak. Yazmadık, unuttunuz.
Nerede?
1 over S.
Burada mı? Here, you mean this one?
Evet.
Okay. Thank you. So now all these can be back transformed. This is 1 over S is 1. Okay. Y of t is the inverse transform of Y of S. Y of t is, now we have 1 over S, which is the back transform is 1, minus, you have S plus 1 over 2. This is exactly this form. So it is e to the minus 1 over 2t cosine root 3 over 2t, right? Now this one is exactly the sine term, but you have the coefficient in front of it. 1 over 3 divided by root 3 over 2 is minus 1 over root 3 e to the minus 1 over 2t sine root 3 over 2t. This is correct for t equals greater than 0. Okay. So we have, if you look at this function y of t versus t, the solution, sorry, y of t, it is actually it's a step response of a system which will look like something like this, as you will see. It is a damped step response, which eventually dies out and comes to a steady state at 1. So this is the response of the system. This is the result, okay? Okay. Do you have any questions?
Hocam, I have a question. This drawing needs to be known, or you draw it because you know it? I mean, or as students, do we have to know this graph, how to draw this graph?
No, not at this point. No, well, I just, I just drew it as a future reference at this point. You don't have to know. You don't know how to, how you interpret it with this, but you will know eventually.
Thank you so much.
Okay.
Hocam,
Yes.
why did it stabilize at 1?
The reason being, there are 3 functions here. One is 1, okay? The second and the third one are exponential decays. These terms go to 0 as t increases. Exponential decays go to 0. Eventually, the response settles at y equals 1. Okay? As time increases, eventually the response goes to 1. That's why.
Okay, thank you hocam.
Okay, we have only 5 minutes left. Any other questions? Next week, I'm going to go on with the electrical systems and other systems, but at this point, let me very briefly talk about transfer functions, okay? Well, I will talk about this later on, but now this is just as an introduction. If you have a system like with a differential equation, let's say differential equation, let's say something like this, y double dot plus 3y dot plus 2y equals, let's say, 2f dot of t plus f of t, let's say, okay? Now, if you want to solve this with Laplace transforms, what do? You just take the Laplace transforms of individual terms and then equate it to 0, equate it to each other. Now, when you try to do it this way, you involve the initial conditions in the problem, okay? Here, if you want to take the Laplace transform, what you do is the following. Let's say s squared plus 3s plus 2 y of s equals, let's say, 2s plus 1 f of s, right? If, by the way, initial conditions are 0. And this is exactly what we do. We ignore the initial conditions. Therefore, we write y of s divided by f of s equals 2s plus 1 divided by s squared plus 3s plus 2, let's say. And this is the, we define this as our transfer function of this system. And basically, this is output divided by the input in the S domain, obviously. In the S domain, so that you can find the response. And we represent it by a block like this. F of s is the input that enters the system, and y of s is the output, okay? And g of s is the thing that transfers f of s, the input, to the output. So that we can represent the system by this. For example, I have given you examples of this, but very simple example is, let's say, a mass spring damper system like this one. Let's say something like this. Let's say the displacement is y of t. There is f of t here. Okay, b. Here, for example, the differential equation that describes this system is y double dot plus, sorry, my double dot plus ey dot plus ky equals f of t. And if you do it, the transfer function g between y of s and f of s, which I will write as g of s, is going to be 1 over ms squared plus bs plus k, for example. Okay, that's all for now. I will elaborate on this, but for now I just introduced the concept of the transfer function. Any questions?
Hocam, may I ask something in Turkish?
Yes.
Yani konudan biraz bağımsız olacak ama genel olarak damping, free damping, over damping, critical damping falan üzerine bir şey soracağım.